Hello everyone, welcome to the second week of the Machine Learning Foundations course. In this week, we will look at the basic math tools that will be required for handling the rest of the course. I have titled it Calculus because that is the majority of this course, and this will majorly overlap with the later part of the Mathematics 2 course that you would have already done. But still this has a different focus. It has a more geometric or a graphical focus rather than the course that you would have seen in Math 2 for data science. So here is a brief overview of this week's content. We'll first take a look at some basic sets and functions that we'll be using throughout the course and notations and the notations for them, and some basic logic statements that we will be making and their math notation for that, and we'll wrap the first part of this week with how to visualize functions, and there are several ways of visualizing these functions, how to graphically visualize these functions. That will be the final part of the first lecture today. Here are some basic sets that you will be using over and over throughout the course. The first set is R, which is simply the set of real numbers, which you would have seen already, and then you have R plus, which is simply the set of real numbers including 0, positive real numbers including 0. Then we have Z, which is simply the set of integers. And Z plus is a set of positive integers including 0. So these are the 4 domain sets that we will very often be using throughout the course. And then there are a couple of other sets that we will use often, which is the closed interval a comma b. This is the set of real numbers such that they are between a and b and the boundaries are inclusive. We include both a and b, so that is the closed interval. Then we have the open interval a comma b, which is simply the set of all x in real, a less than x less than b. The only difference between these two sets is that in the second set the boundary points a and b are not included. So all of these sets can be exponentiated to power d, right? The Cartesian product d times will be taken. For example, you can have Rd is simply the set of d dimensional vectors. So Rd is the same as writing R cross d times. An example element in, for example, R3 would be, let's say 1, 2, 3.3 is an element in R3. You can have this power, Cartesian product power, to pretty much any set that you can think of. For example, you can have a comma b power d is simply the set of d-dimensional vectors, but each element in the d-dimensional vector is going to be between a and b. So you can write this compactly as the set of d-dimensional vectors in Rd such that xi belongs to the closed interval a comma b, for all I belongs to 1, 2, So these are some of the sets, the basic sets that we will notate throughout the course. The next object that we will be interested in analyzing is a metric space. So what is a metric space? A metric space is simply a set with an extra structure associated with it, and the main that structure is the distance function. So you can have a distance function d which takes in 2 objects in the set. That is the distance function. So the default metric space that we will be working throughout is Rd, which is the d-dimensional vectors, with the distance function simply given by the Euclidean distance. By that I mean d of x comma y is simply the norm of x minus y, which is simply the square root of x1 minus y1 the whole squared plus dot 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 xd minus yd the whole square. So, this is the standard Euclidean norm. This will be the default metric space for most of our course. This metric, there is a crucial set that is associated with metric space, which is a ball. Right? We can define an open ball of radius epsilon centered at x, that is given by b of x comma epsilon, is simply the set of y in Rd such that the distance of y from x is strictly less than epsilon. This is the open ball, where we have some x is some element in Rd and ball of x comma epsilon is simply the ball of radius epsilon centered at x. Sometimes we will also be using the closed ball, we are also using the closed ball, which is b bar of x comma epsilon, which is the set of y in Rd such that d of x comma y is less than or equal to epsilon. The only difference between the open ball and the closed ball is that the open ball does not contain the boundary, the closed ball does contain the boundary. What do I mean by that? Here is a simple example for the set. So, imagine you are in d-dimensional, d equal to 2 space, 2-dimensional space, and let us say for example x is the vector 1 comma 1. Right. So, here this gray set is the ball of centered at 1 comma 1 and radius let us say 0.5. Right. This is the open ball if you do not include the black boundary, and it is actually equal to the closed ball if you include the boundary. So, if you do not include the boundary, it is the open ball. If you include the boundary, it is the closed ball. Right. This is an example of a ball of radius, of a given radius around a given center. The ball will be a very crucial part for doing a lot of analysis with metric spaces. Okay. So, now we move to another crucial aspect of the math that we will do here, which is some sets and logic. Right. So, you might have seen Venn diagrams in your school itself, but we will still do a quick recap of that. Right. So, you have sets living in a universe. Right. So, that universe let us denote it by the set V. V is the universe, and you have let us say sets A and B which contain elements in the universe. The basic operations that are associated with sets are union and intersection. So, you can have V is the universe, you can have A union B, A intersection B, and A complement and B complement. So, these are some of the basic sets associated with a given pair of sets A and B. A union B is simply the union of both A and B. For example, if this was A and this was B, A union B is simply the entire all elements in A and B. A intersection B is the elements that are in both A and B. A complement is simply the set of elements in the universe but not in A, and similarly B complement. So, you can in principle write A complement as the universe set difference A. Right. So, this is another notation that you might want to know. This is the notion for set difference. So, how do you denote the difference between two sets? This is a backslash symbol, that is A complement. Similarly, you can have B complement also. With the Venn diagram, you might have seen the De Morgan's laws, which are the basic laws of logic essentially. What does it say? Well, it is a collection of pair of two equations, which is A union B, the whole complement is simply equal to A complement intersection B complement, and similarly A intersection B, the whole complement is equal to A complement union B complement. Graphically, this is pretty easy to understand. A union B, the whole complement, is simply the elements that are in the universe but neither in A nor in B. So, that is essentially the unshaded region of this diagram forms A union B, the whole complement. That is clearly exactly equal to A complement intersection B complement. Right. So, that is the first law, and similarly you have the second law. A intersection B, the whole complement, is simply the set except for this intersection. That is A intersection B, the whole complement, and that is clearly exactly equal to A complement union B complement. That is we'll see this with a very simple example. Right? Let's say your universe V is the closed interval 0, 10. Right? This is the universe here. Let's say we have two sets A. A is equal to the closed interval, let's say 2, 5, and let's say B is the closed interval given by 4, 7. Right. So we have A as the closed interval 2, 5 and B as the closed interval 4, 7. Now let's just quickly verify the De Morgan's laws here. What is A union B? With this we can say what is A union B? A union B is the interval 2, 5 union the interval 4, 7, which is clearly the interval 2, 7. Right. What is A intersection B? It is clearly the closed interval 4, 5. So what is A union B the whole complement? A union B the whole complement is simply the set 0, the closed interval 0, 10 difference the set 2, 7, and that is simply given by the union of this set, the 0, 2 union 7, 10. Right. Note that I am using closed square brackets for 0 and 10, but parenthesis for 2 and 7 because 2 and 7 are not included in A union B the whole complement. Right. So, you can clearly see A union B the whole complement is 0, 2 union 7, 10 with parenthesis for 2 and 7. This is clearly equal to A complement intersection B complement. Why is that? A complement is simply we will just verify that quickly. What is A complement? Well, A complement is the set 0, 2 union 5, 10, and B complement is simply the set 0, 4 union 7, 10. The intersection of A complement and B complement is exactly equal to A union B the whole complement. So, this is a pretty simple way to simple verification. You can do a similar verification for A intersection B the whole complement also. So, this is the De Morgan laws and the basic set operations that you will need to be familiar and comfortable with. So, and there is some logic statements that we will also be using throughout the course, and the four main types of logic modifiers that you will see are these. First is you have inverted A, which is said to mean for all, and you have an inverted E, which means there exists, and then you have the arrow marks. This the double-sided arrow mark essentially means implies, and you might see a two-sided arrow mark which is saying equivalent to. So, you can say A arrow B, if A and B are two statements, you can say A arrow B is equivalent to saying that A implies B. You can have two-sided arrows, which means that A is equivalent to B. A implies B and B implies A, then we have a two-sided arrow. Right. So, we will illustrate all these logic statements through another building block of analysis and calculus, which is sequences. What is a sequence? A sequence is simply an ordered collection of elements, that is a sequence. Here is an example sequence. Here is a collection of elements. In each of these elements are going to lie in R2. Right? Xn is 1 plus 4 by 2 power n, 3 minus 4 by 2 power n. First, you can see that each of these elements are two dimensional. So, these elements are in R2. What, for example, let us say set n equal to 1. If we set n equal to 1, x1 is simply 1 plus 2, 3 minus 2, which is 3, 1, which is this element here. You can then substitute n equal to 2, you would get 1 plus 2, 1 plus 1, 3 minus 1, which is 2, 2. And you can keep on increasing n, and let us say for large enough n, you can see that 1 plus 4 by 2 power n is approximately going to be equal to 1, and 3 minus 4 by 2 power n is approximately going to be equal to 3. So, if you this is the first element is x1, the second element is x2, and you can keep on doing this. As your n increases, you can see that the xn seems to approach this point, the red point here, which is simply 1 comma 3. This is an example of a sequence, and another example of a sequence would be, let us say, this sequence where xn is cosine of pi by 2n comma sine of pi by 2n. This sequence also, each element here lies in R2, and this is similar to the previous sequence which also lied, each element lied in R2. But this sequence, you can see, is going to be very different. Let us just try to do that, right. So, what is x1? x1 is simply cosine of pi by 2 comma sine of pi by 2, which is 0 comma 1. What about x2? x2 is cosine pi comma sine pi, which is this. What about x3 is going to be this, x4 is going to be this, and x5 is again going to be exactly equal to x1 because of the periodicity of cosine and sine. So, now this is also a valid sequence, but you can see that this sequence does not seem to converge towards any particular point. So, I will make the notion of convergence clear soon, but you can see the difference between this sequence and this sequence. So, the first sequence, as the n essentially increases, you have your xn be a constant, but in the second sequence, as n increases, it does not seem to stay still, it keeps on moving. So, this gives us the first important definition of a sequence, which is convergence or limit. So, you can say that, let us say you have a sequence x1, x2 dot dot dot, where xi are d-dimensional vectors. We can say that limit I approaches infinity, xi is equal to x star if there exists an epsilon greater than 0, if for all epsilon greater than 0 there exists an integer n such that your x small n belongs to the ball centered at x star comma epsilon for all n greater than or equal to capital N. This is the equivalent, it is a definition here, so you can have a two-sided arrow. When someone says the limit of the sequence is x star, what they mean technically is this statement. We will try to parse this statement quickly. What does this say? This says that for whatever small epsilon that you choose, there exists some number integer n such that after that integer your xn is going to stay within a ball of radius epsilon centered at x star. Let us try to check that for the first sequence that we had here. Right? Whatever epsilon you choose, which means that however small a ball that you can choose around x star, you can see that after some large enough n, your xn's are going to stay inside that ball. Right? You can choose however small radius that you want. You can choose a radius of 0.1, 0.01, 0.001. You can choose whatever radius around x star, which is in this case 1 comma 3. You can consider a circle or a ball of radius epsilon around 1 comma 3, and eventually your sequence is going to go inside that ball and stay inside that ball. It is not going to go out of the ball at all. This is going to be true for whatever radius that you choose, as long as radius is greater than 0. So, this means that this particular sequence here converges to 1 comma 3, or in other words, limit I approaching infinity xi is equal to 1 comma 3. So, that is this is an example of a convergent sequence. You cannot say the same for the second sequence. For example, I can draw a ball of radius, let us say 0.1 around any point that you can think of. Let us say I draw a ball of radius 0.1 around this point. Yes, occasionally your sequence does go inside this ball, but it also goes out. It never stays completely inside the ball after a point. Right? So, this particular sequence, the second sequence, does not converge to any point at all. So, this is an example of a non-convergent sequence. So, the idea of a limit, and this also explains the logic. Right? So this says for all epsilon, which means that however small a radius that you choose, there exists a point beyond which your sequence stays inside that ball of radius epsilon centered at x star. This is equivalent to saying that the limit I approaching infinity xi is equal to x star, or you might also write this as simply xi approaches x star. This is another alternate notation for writing this, where your xi tends to x star or xi approaches x star, limit I approaching infinity xi is equal to x star. All these are equivalent statements for the same mathematical fact. Okay. So, here are a couple of exercise problems for you to think about. Here is one. So, for each of these example sequences, think what would a converge, does the sequence converge or not? If it does converge, what is the convergent point? Right? So, let us say your first sequence xi is just real value, not even R2, just real value. What is xn? Xn is simply equal to, let us say, 1 plus n. So, does this sequence have a convergent point? Does it converge to anything? That is the first question. The second question is, let us say your xi are 2-dimensional vectors xi in R2, and let us say your xn is given by 1 by 2 power n cosine of pi by 2 n, comma 1 by 2 power n sine of pi by 2 n. This sequence looks similar to the non-convergent sequence we saw earlier, but just that now you have a 1 by 2 power n on top of it. Does this sequence converge to anything? Then finally you have a third sequence xi R2, where your xn is simply given by 1 by 2 power n cosine of pi by 2 n, but the second coordinate is different, it is just sine of pi by 2 n. Just think about these three sequences, and do these three sequences have a limit? Do they converge to anything? If so, what? If not, can you show that? Can you show that these three sequences, these sequences do not converge to anything? This is a pretty simple exercise. I hope you can do this. Right. So now we'll move on to the next fundamental building block of this course, which is a vector space. A vector space is also similar to a metric space in the sense that it is also a set with an extra structure associated with it. Vector space, you can simply call it as a collection of vectors, but not any arbitrary collection of vectors. This collection of vectors must satisfy certain properties. There are several properties, but the most important property is as follows. Say if V is a vector space, then this particular property must hold. There are other properties, but this is the most crucial property. You have, let us say, an element u belongs to V, and let us say you have another element V also belongs to V. Let us say alpha comma beta are some arbitrary real valued scalars. If V is a vector space, capital V is a vector space, then any linear combination of its elements is also in the set. Right? That is, you have alpha u plus beta v also belongs to the vector space. This is the most crucial requirement of a vector space. There are other requirements also, but this is the most important one. And for our purposes, the most important vector space is simply going to be Rd. Rd is a vector space. Why is that? This is kind of obvious to see. Let us say you have two 3-dimensional vectors. If you add them, the output is also clearly a 3-dimensional vector. Let us say you have two 3-dimensional vectors u and v, 5 times u plus 7 times v is also a 3-dimensional vector. So, Rd is clearly a vector space according to this definition at least. It also satisfies all the other requirements of a vector space. Sometimes a vector space is also associated with what is called a dot product or an inner product. You have, for example, let us say a vector let us say x and y belong to the vector space V, then x dot y is equal to x transpose y is simply sum over I equal to 1 to d xi yi. This is the dot product of two vectors in the vector space, and this is the dot product. The norm of a vector squared, norm squared is simply given by x dot x or x transpose x, which is simply sum over I equal to 1 to d xi square. The vector space can also have these two properties, attributes associated with it, which is the dot product or the inner product and the norm. For our purposes, we will mostly be working with RD or subsets of it. So, our vector space will always have a dot product and a norm. One notion that will be very often useful for us with vector spaces is the notion of perpendicularity or orthogonality. Let us say you have two elements x and y in a vector space. We will say x and y are perpendicular or orthogonal to each other. Are orthogonal to each other if x dot y, which is equal to x transpose y, which is equal to sigma xi yi equal to 0. If you have the dot product of two vectors is equal to 0, then we will call these two vectors as orthogonal or perpendicular to each other. Right. Now, moving on to the other important building block of our course, which is functions. Functions are simply mappings from one set to another set. So, a function f, let us say, is a mapping from A to B. A and B are sets. A is called the domain of the function f and B is called the codomain of the function f. When we say real valued functions, we mean the codomain of that function is R. We will be working mostly with the real valued functions. Say one dimensional function means that will be a function from reals to reals. That is, the domain is R1 and codomain is also R1. We will often also be working with d-dimensional functions or multivariate functions, where the function f is a mapping from Rd to R. So, that is a function. A function is simply a mapping from the domain to its codomain. Sometimes for visualization purposes, it is also nice to have a graph of a function. What is a graph of a function? A graph of a function is a subset. Right? So, if you have a function f from Rd to R, the graph of this function, let us call it Gf, is a subset of Rd plus 1. Gf is simply the set of x comma f of x such that x is in Rd. The graph of a function is you vary your input over the domain and you concatenate your input, which is an Rt. This is a d-dimensional vector, this is a scalar. So, if you concatenate a d-dimensional vector and a scalar, you get a d plus 1 dimensional vector. So, that is why this is a subset of the graph of a function f is a subset of Rt plus 1. So, here are simple illustrations of visualizing simple functions first. Now, one dimensional function, let us say you have one dimensional function f from R to R. The easiest way to visualize that is a simple plot, right, where you just have an x axis where you try different inputs and on the y axis you simply plot f of x. So, you, for example, in this case this function is simply f of x is equal to x squared. So, a very simple function, and you can easily visualize this by a plot. It is possible to do that for one-dimensional functions. And what is the graph of this function? The graph of this function is a subset of R2 now, because f is a function from R to R. The graph of this function is a subset of R2, and GF is simply equal to x comma x squared such that x belongs to R. It is a subset of R2, but really it's just a, you can imagine the graph on a paper corresponds to where all you have ink on the paper for this curve corresponds to a subset of R2, and that is the graph of this function. Things become a little bit harder with two-dimensional functions. That is, if you have a two-dimensional function, that is f is from R2 to R. It is no longer possible to easily plot it because you will need one more dimension, and paper is just 2 dimension. Papers or screens are just 2 dimension. You can't really plot this such a function. And 2-dimensional functions are really very useful for going beyond 1D, and they are the simplest illustrations which are non-trivial in most situations. And so it is nice to have a way to visualize 2-dimensional functions, and the standard way to visualize a 2-dimensional function is to use contour plots. So what do we mean by that? Let us say we have a simple function f from R2 to R. Let us say f of x is equal to x1 plus x2. So x is a 2-dimensional vector, which means that there has 2 components x1 and x2. F of x is, let us say, x1 plus x2. How do you visualize this function? The standard way to visualize this function is to think of a set of values the output of this function can take. For example, let us say the values that you are going to give are, let us say, -1, 0, 1. It can be more values also, but for now let us just say -1, 0, 1. What do we mean by that? We take the function f and we set f of x to be equal to -1. We essentially consider all solutions of this x and plot that as a curve. Right? So when you set f of x is equal to -1, which means that x1 plus x2 is equal to -1, which x1 is equal to minus x2 minus 1. So which means that x1, so if you plot all x1 comma x2 which satisfy this constraint, you would simply get this curve. In particular, it would pass through the points given by 0 comma -1 and -1 comma 0. Let us label this particular red line by the contour f is equal to -1. Similarly, you can do that for other values in the value set, which is f of x is equal to 0 implies x1 is equal to x2. Sorry, x1 is equal to minus x2. And that would correspond to this set. We will label this also by the appropriate contour, which is f is equal to 0. And similarly, you can have f equal to 1 would correspond to this set. I am not being particularly neat in drawing these figures, but this should give you an idea of what we mean by contours. So these, for example, you could have more values here. You could have -1, 0, 1, 2, 3, 4, 5. You would have more contours. So each of these lines are called contours, and this might remind you of something which you would have done in your geography in your school. For example, you might have plotted isotherms or isobars, which are lines of constant temperature or lines of constant pressure. Those are exactly contour plots. Contour plots are the standard way to visualize 2D functions. Here is a contour plot of a slightly more complicated function. where f of x is equal to x1 into x2. Right. So, you can see that if x1 into x2 is set to 0, that means that x1 is equal to 0 or x2 equal to 0. That is why you have this particular contour labeled by 0. You can, for example, set f of x is equal to 10 and you would get this particular 4 contours. So, you can have 1 comma 10 is a valid way of getting 10, minus 1 comma minus 10 is also valid. So, this both of these put together form the contour for f equal to 10. Similarly, you can get f equal to minus 10 would correspond to these two contours. This is a contour plot, and sometimes it is nice to actually add color to a contour plot. Technically speaking, you do not need color for a contour plot. You could just draw lines and label each contour by its value, but you could have colors also. In this case, what I have done is you can see that yellow corresponds to high values and purple corresponds to low values, and each contour has the same color. Technically speaking, you could increase the number of contours to really large numbers. Instead of here I have drawn contours for 0, 10, 20, 30, 40, 50, 60, 70, 80, 90 and then minus 10, minus 20, minus 30, minus 40 and so on. But there is nothing stopping you from drawing more contours for, let us say 0, 1, 2, 3, 4, 5 or 0, 1, 1.1, 1.2. If you drew enough contours, you would fill the entire region. If you drew enough colored contours, you would fill the entire region, and that would correspond to this particular figure on the left here. So, this figure is called a heat map, and the figure on the right is a contour map. So, both have the heat map essentially gives you more information than the contour map, but sometimes it might be difficult to see the geometric shape of the contours from the heat map. For example, here it is not so easy to see that the shape of the contours are these curves. Contour map gives that information, but the heat map technically contains more information about the function because it is infinitely many contours are there in the heat map. Here is one other example of another function where f of x1 comma x2 is simply x1 squared plus x2 squared. You can see that the contours are circles and the heat map also looks circular, vaguely circular in shape. This is the heat map and this is a contour map. So, these are two standard ways to visualize 2D functions. With that, I think we can wrap up the basic setup and basic notation and symbols and visualization techniques that you will need for the rest of this week and for the rest of the course also.